Okay, let's start with this question number 1. Let R and RQ denote the set of real numbers and the three-dimensional vector space respectively. The value of alpha for which the set of vector does not form a basis of RQ. So all these vector that belongs to this three-dimensional space. This info has given, and also you can look at that each vector has how many components? 3 components. So you can say these set of vectors belongs to some three-dimensional space. And about this information that are all those components will be a real number. So alpha will be here a real number also, and all those given components are a real number. So we have to find alpha such a way that these set of vector should not form a basis of RQ. First of all, you need to have the understanding of this basis. What is basis? So basis is a set of vector, and in those set of vector, all those vectors will be independent, right? So if this set of vectors, so this is given a set, right? In this set we have 3 vectors. So if it is a basis, if this set is a basis, then all these 3 vectors should be independent. But we have to find the condition such a way that this should not form the basis. That means these set of vectors should not be independent, right? So if these set of vectors are independent, and if we try to find the determinant of it, then obviously if one of the vector is depending on some other vector, or one of the vector is a linear combination of some other vector, then their determinant would be 0. So simply what we conclude, that we just need to find the determinant, and we will have the condition. This way we can also find, and another way we can do even proceed with the elimination, and after proceeding with the elimination we can find that way also. So let's first of all proceed with the elimination. So what we can do, we can have this 2 minus 3 and alpha. This we can consider at is a maybe column vector or a row vector. So let's consider it as a row vectors. So 3 minus 1 and 3, and 1 minus 5 and 7. So let's say that this forms a matrix, and we can proceed with the elimination. We can consider this as a pivot, and we can eliminate these 2 guy, this one and this one. So what operation we will perform? We will perform R2 minus 3 divided by 2 R1, that will go to R2. This is the first operation, and second operation is R3 minus 1 divided by 2 R1, that will go to R3, right? And here this is not the negative sign. Let me write it clearly. Okay, so we can do this operation, and once we do this operation we will have first row as it is, because we have done nothing to first row. Second row, here it will be definitely 0, because you can check also that, because we have applied this operation such a way that it should be 0, right? So R2 is here 3 minus 3 divided by 2 into R1 is 2. So 2 cancel, 3 minus 3, that will be 0. So 0. Here also it will be 0. You can cross check it just to verify. 1 minus 1 divided by 2 into R1 is 2. So 2 will get cancelled. 1 minus 1 is 0. That will go to R3. What will be here? Here it will be minus 1 minus 3 divided by 2 into R1 is minus 3, right? So overall it will be minus 2 and plus 9, that will be 7 divided by 2. So here we will have 7 divided by 2, and here we will have 5 minus 1 divided by 2 into R1 is minus 3. So minus 10 plus 3 divided by 2, that will give you minus 7 divided by 2. right? And here also we can do the operations like 3 minus 3 divided by 2, and r1 is alpha, so 6 minus 3 alpha divided by 2. What will be here? 7 minus, so here it will be 14 minus alpha divided by 2, right? So now we can consider this as a second pivot and we can proceed with the further elimination. So what we will do, we will try to eliminate this guy. 2 minus 3 alpha and 0 minus 7 by 2, because we have done nothing to first row and second row. And what operation we are applying here is r3 plus r1, sorry, r2, that will go to r3, right? So here it will be 0, here it will be 0, and here it will be 6 plus 14, that will be 20, and minus 4 alpha divided by 2, right? Now if these set of vectors forms a basis, then we should not get 3 pivot, because if we are getting the 3 pivot, then definitely all these 3 are independent, but we should not get a 3 pivot. That's why here, so we have already got the 2 pivot, right? This is the first pivot and this is the second pivot. So what will be the condition? So that these set of vectors should not form a basis, we should not have a 3 pivot, right? If we should not have 3 pivot, we are having less pivot. We have originally we were having 3 vectors, and if these 3 vectors are independent, then obviously we will get the 3 pivot. But if we have to find this should not form a basis, that means 20 minus 4 alpha divided by 2, that should be equal to 0 in order to get only 2 pivots. If it is 0, then 0 cannot be a pivot, right? So from here what you can say, that 4 alpha is equals to 20, so alpha is equals to 5, right? And this is the one way to do that. And another way how you can do that, you can just proceed with the determinant, and determinant should be equal to 0, right? Because if these set of vectors are independent, so dependent, then their determinant is going to be 0, because one of the row will be depending on, or one of the row will be linear combination of other rows, so that is why determinant would be 0 in order to not have a basis with these set of vector. Shall we do that? Let's proceed and let's do the second method also, so that you have the clear picture without having any kind of doubt. So this is the first method we have done, and now let's look at the second method. So the goal of this lecture is to just to have you a clarity and the confidence in the exam. The goal of lecture is to not just like sake of the completion, right? You should have the confidence, so that you can execute anyway whatever comes first in your mind in the examination, right? So we can just proceed and we can just take the determinant of this. So what will be the determinant of this? So 2 will be here. So minus 1 and plus, sorry, minus 7 plus 15, so that will be 8, right? And plus 3, so 21 minus 3, that will give you 18, and plus alpha, so minus 15 plus 1, that will give you minus 14, that is equal to 0, right? So 16 plus 54 minus 14 alpha is equals to 0. So from here what we can say, 14 alpha is equals to that would be 70, and from here alpha is equals to 5, right? So you are getting the same answer anyway, right? So you should get you should have the idea of this basis. What is this basis? So basis for a vector space is a set of vectors, and if we are saying that set of vector is a basis of a vector space, then those set of vectors will be independent. And if it is independent, then we should not have the more pivot or the less pivot than the number of vector. Or if we think in terms of the determinant, then those set of vector forms a basis, then their determinant would be not equals to 0. Okay, now let's look at this question number 2. Consider this matrix where k is a positive real number. So k is a positive real number. Which of the following is a eigenvectors of this matrix? So by looking at this matrix, the first point I would like to check, what if this matrix is a symmetric matrix. So in this case, the value of k would be 2. And why I am checking for this symmetric matrix? Because I know about this symmetric matrix that symmetric matrices have the orthogonal eigenvectors corresponding to different eigen value. So if this is a symmetric matrix where k is equals to 2, if we take this k is equals to 2, then this will be a symmetric matrix. Then definitely I should get two eigenvalues. I think two different eigenvalue I will get, because the sum is 2, that sum of the eigenvalue is 2, and what will be the product? So product will be 1 minus 4, that is minus 3, right? So sum is 2 and product is minus 3. So what will be the eigenvalues? The eigenvalue will be different, right? So in this case I will have two different eigenvalue, and since this matrix is symmetric matrix, so definitely I will have the eigenvectors that will be perpendicular to each other. That means if I take the dot product of those vector, those will be 0, right? So by looking at this option A, B, C, D, if we take the dot product of these two vector, so k is here 2, right? So 2 1 dot product with this 2 minus 1, so what we will get is 4 minus 1, that is 3. So these two vectors cannot be the eigenvector. We can check these two also. So 1 minus k is 2, so that will be minus 1, and this will be, so I am taking the dot product with this 1 and 2, sorry 1 and 1. So the dot product will be 0, right? Because 1 into 1, that is 1, minus 1, that is 0. So these two can be our eigenvector. Let's check for others also. We can even take these two as the eigenvector, so that will be 1 and 1, and this will be 2, right? Because no, yes, k is 2, so 2 into 2 4, and square root of 4 would be 2. Here it will have 1, right? So and if we take the dot product, we are not going to get the 0, right? We can even check with these two. So 1 and minus 1, that is the first vector, and the second vector would be 2 1, right? So definitely we will be not getting 0. So I am 100% sure that these two options are the correct option. So A and B. Right? So the here examiner just wanted to check you with the symmetric matrices. So he gave you this matrix. So only one element is unknown, and with these options you have to play, and you just have to keep this fact in a mind that symmetric matrices have the orthogonal eigenvector corresponding to different eigen value. Okay, now let's look at next question, that is question number 3 according to our sequence. So we have given this set of matrices. We just need to find that which of the following matrix has an inverse. So which matrix you can do the inverse. So the very first thing what you will do, you will just look at the rows and column. You will try to find any kind of dependency is there or not, right? if any matrix is given in front of you, either you have to find the determinant, if you have to do any operation, just go through it, just check the dependency. If there is any visible directly to you, it is okay, that would be a good thing to you, right? Because that way you will save the time. You just have to find which of the matrix is invertible. If there is dependency in column or rows, then definitely that is not going to be the matrix that is invertible, right? So we will just look at, first of all, this matrix A, just look row wise. If there is any kind of dependency, that one row is depending on linear combination of the some other row, if it is, then this is not going to be the invertible one. So just look at the row. So this is 1 4 8 0 4 2. So you can directly say this third row, if you multiply with this 2, then you will get the first row. So if row 3 is there, and if you multiply the row 3 with the 3, then you will get this row 1. You can do that. So not with the 3 multiple, but with the 2, right? So 0.5 into 2, what you will get? 1. 2 into 2, 4. 4 into 2, 8. So that means this matrix is not invertible. And even if you have not found any dependency row in row vector, then after that you just look quickly at the column vector. Maybe in column you will quickly find the dependency, right? So that is the first check you should do. So this will not be invertible, right? And the second matrix, you can see, you can just look at the row 1 2 3 2 4 6 and 3 2 9. So 1 2 3 is there, and if I, yes, so you see that if I multiply the first row with the 2, you will get the second row. Multiply 1 times 2, that will 2, 2 times 2 4, 3 times 2, that will 6. So this matrix is also not invertible. Now let's look at this option C. So in option C, let's look at this first of all row wise. So if you look at row wise, 1 4 8 0 4 2, I'm not getting, so I will just directly jump to columns. So let's look at this, if these columns have any kind of dependency. No, I am not able to see it directly. Maybe there would be, but I will directly jump to this option D. So option D, let's look at the rows first. So yes, if you multiply this first row 3, then you will get this row 3. Multiply the first row with the 3, then you will get this row 3. So 1 times 3 is 3, 4 times 3 is 12, 8 times 3 is 24. So this one is also not going to be the invertible one. So I do not need to check for the C, because C is the correct answer. Now this question number 4, the sum of the eigenvalues of this matrix is. So this matrix A is equals to 2 by 2 मैट्रिक्स है, स्क्वायर है, आइगन सम ऑफ आइगन वैल्यू पूछ रहा है. That means just we can 2 by 2 matrix is there, so just we can multiply and we can add the diagonal elements of this is matrix, then we will have the eigen sum of the eigen value, right? So that's a easy one. So what you have to do, you just need to perform the matrix multiplication and add the diagonal element. You will get your sum of the eigenvalue. So if we multiply this, so here we will have 1 plus 6, that will be 7, and 2 plus 8, that will be 10, and 3 plus 12, that will be 15, and 6 plus 8, no sorry, 6 plus 16, that will be 22, right? And we have to find the sum of the eigenvalue. So sum of the eigenvalue is nothing but the sum of this diagonal element, that will give you the sum of the eigenvalues. So that is 7 plus 22, that is 29. So the answer is 29 for this question. Now this question number 5 is again easy one. So what is the eigenvalue of this matrix? We have given these 4 options. So we have to just find the eigenvalues, and what we can do, we can just find using trace and determinant, right? We can go through the options and we can just select which option is correct one, because if you look at the trace of this matrix, that would be 4 plus 2 6 plus 2 8. So sum of this eigenvalue should be 8. So 5 plus 2 7 plus 1 is 8, 4 plus 3 is 7 plus 1 is 8, and this will not be 8. The sum of these will not be 8, so C or D cannot be option, right? And next what we can do, we can find the product of the eigenvalues. And what are the product of the eigenvalues? So product of eigenvalue is nothing but the determinant of this matrix. So what will be the determinant of this matrix? 2 times 4 8 minus 1 is 7, right? So 2 times 7 minus 1. Here we will have 2 minus 1, that is 1, again plus 1, and here we will have 1 minus 4, that is minus 3. So that is 14 minus 1 minus 3, that is 10. So the product of these eigenvalues should be 10. So if you multiply these, so 2 times 5 is 10 times 1 is 10, right? And if you multiply this one, that would be 12. So the correct answer for this question is A. So this was a very easy question. Okay, now let's look at this question number 6. This question is also easy. So we have given two matrices, two rectangular matrices A and B, and we just need to find the determinant of the multiplication of these matrices. So I think yes, we will have to do the multiplication. So we can just find this matrix A times B. So what will be the matrix multiplication A times B? So that will be minus 2 plus 2 and plus 4, that will be 4. And here we will have 0 plus 3 and plus 16, that will give you 19. And here we will have minus 1 plus 3, that will be 2. And here we will have 0 0 and 12, and the determinant of this matrix will be 48 minus 38, that will give you 10. So and now let's look at this next question, question number 7. So we have given this matrix and we just have to find the product of all eigenvalues of this matrix. So what is the product of all eigenvalues? The product of all eigenvalues is nothing but the determinant of this matrix. And again I will say, before calculating the determinant, just have a overview of the matrix. Just look at the columns, just look at the rows vector, just look at the columns vector, and if you can find any dependency within 10 to 15 seconds, it is okay. Otherwise anyhow we will be calculating the determinant. So first let's look at the rows. So while looking at the row, so 7 is here. So I think if I multiply this row, second row, by 2, so that will be 8 and 10 and 12, right? And if I subtract the third row from this, so that will be, say, third row is 7 8 9, right? So I will get the first row. 8 10 minus 8 is 2, and here we will have 3, right? So you see, by looking at the rows I find the dependency. Sometimes you will find easily the dependency on the columns. So whatever you are comfortable with, first looking at the rows or the columns. So since these rows vector are not independent, it has some dependency, because this first row is the linear combination of this second or third row. So yeah, the determinant of this matrix will be 0, right? So determinant of this matrix will be 0. That means the product of the eigenvalues will be 0, because one of the eigenvalue will be 0, right? And once we do the product of all those eigenvalue, what you will get is the 0. So the correct answer for this option B. Okay, now let's look at this question number 8. So let A be any n cross m. So here n represents the number of rows and m represents the number of columns. Where m is greater than n, that means number of columns is greater than number of rows. So what kind of shape you will get? You will get a matrix that will be shorter and wider, right? So we will have maybe 1 2 3 4 5 columns and with only 2 rows, and the rows are represented by this number, that is n, and columns has been represented by this number, that is m. Right, now next we have to look at the true statements about the system of linear equation, that is Ax is equals to 0. So basically, proceeding with this particular question, you should have a good understanding of solving the system Ax is equals to 0. What info you should have? You should know that what is pivot column or pivot variable. You should have the info about free column or free variable. You should have info about how to find the null space. Yes, you should have the info that how to what's the procedure for finding the null space. If you have these infos, then you are good with this question. Otherwise, you will have difficulties. Alright, so we have the shape of matrix. We have to basically, I think, look at the null space. So let's look at the first option. There exists at least m minus n linearly independent solution to this system. So basically, first of all, you have to understand what this statement A is saying. So this statement A is saying that in the null space you will have at least m minus n vectors that will represent the complete null space, right? So if you know how to find the null space, you can instantly give this answer, because the number of vectors that are linearly independent and that are in the null space depends on how many free columns you have in this matrix. And how can you find the free columns in the matrix? It is easy. You have this matrix A, you can proceed with the elimination, you will get some kind of upper triangular matrix. Let's suppose you have proceeded with the elimination, and since it is talking about at least, so I am saying that you have got at most pivot element. Let's suppose you have got maximum number of pivot. So what is the maximum number of pivots you can get for this kind of matrix? That depends on number of rows, right? Because number of row is less and each column or row contains only one pivot, so maximum number of pivot we can get is 2 for this particular matrix, right? And the columns which does not contains the pivot and which have no pivot is called the free column. So these are the free columns, and corresponding to these free columns, whatever the variable you will have associated with this column, you will call those variables as a free variable, right? So this first column is associated with x1 variable, second with x2, x3 and so on, right? So this x3, x4 and x5 are the free variables, right? And this number of free columns, this gives you number that how many linearly independent vectors will be in the null space, and those set of vectors will represent the complete null space, right? So according to statement A, what it says that there exists at least. So yes, if we have maximum, if we are talking about maximum number of pivots in a matrix, for this matrix, then yes, we will have at least m minus 1 free variables, and so corresponding to these free variables we will have m minus n 3 linearly independent vectors in a null space that are going to represent the solution of this system. So this statement is true, right? And if you are not able to get my points, then I would definitely suggest to go through my lectures for how to solve Ax is equals to 0, or how to solve the system of equation Ax is equals to 0. I have talked in very detailed manner that what is this pivot column, free columns, what's the procedure of finding the null space, right? So if you know all these points, this question you can solve this instantly, right? Okay, now coming to this statement B, there exists m minus n linearly independent vector such that every solution is a linear combination of these vector. So this statement is false. If it would have given here that there exists at least m minus n linearly independent, then this statement will be true. If here it is mentioned that at least, but it says that exactly m minus n linearly independent vectors is representing the complete solution space. So what it is saying, that there exists a m minus n number of vectors in a solution space. Exactly, there exist m minus n vectors in a solution space, and their linear combination will represent the complete null space or the solution space. But this could be a case when we have maximum number of pivots, when we have achieved the maximum number of pivots, but we have nothing given about the pivot and all this thing info. So there would be case that we can have more than m minus n number of free columns, right? Maybe for this particular matrix I will get this only one pivot, and then how many number of free columns we will have? We will have total 1 2 3 4 columns, that is number of free columns, right? So, and if you try to find here that m minus n, so m is here 5 and n is here 2, so that will be 3, right? But how many vectors we are getting here? How many free columns we are getting here? 4, right? So it can be a case that we are getting just one pivot for this particular size of matrix. Then here we will have 4 number of vectors, 4 free column vector or 4 free variables, and corresponding to that we will have the 4 independent vector in the null space, and their linear combination will represent the complete null space. But here it is saying that exactly m minus 1, and it doesn't mention here at least, so we are considering that it is saying that m minus n linearly independent vector represents the complete solution space. So that statement is false. I think you have got the point. So overall point why this statement B is false, because maybe we can have this just one pivot. In this case we will have more than m minus 1 free columns, so that is why this statement B is false. Coming to this statement C, there exist non-zeros. So there exist non-zero, so obviously we are not talking about the solution for which x is 0, right? That is very like obvious case or the trivial case if you consider x is equals to 0, right? So obviously we are not talking about this. So we are talking about only non-zero solutions. So there exists a non-zero solution in which at least m minus n variables are 0. So m minus n variables are 0. So this statement is also false, right? So if you know how to solve or how to find the null space, then instantly in your mind it will hit that that at least m minus 1, because what will happen? So let's suppose for this particular matrix, let me give you the picture here. So 1 2 3 4 5, right? So maybe here we will get the pivot, here we will get the pivot. So this column corresponds to x1 variable, this x2, x3 and x4, and x5, right? And if you try to find the non-zero solution, right? So how we proceed with finding the null space? What we do, we see that how many free variables we have. We have three free variables. That means we will have three spatial solution, right? So let's first find out the first spatial solution. To find out the first spatial solution, what we do, we try to set one of the free variable as 1 and other free variables as 0. So x4 will be 0 and x5 will be 0. So we try to set with this variable. So we are just finding one spatial solution. How many spatial solution we will have? We will have such kind of 3 spatial solution, right? So once you set this, right, so what you have done is you have set this x3 1, x4 0, x5 0, right? And you will get x2 some non-zero, so obviously you will get some maybe or x1 some non-zero. That could be case. Even you can get the 0, but non-zero is also possible, right? So you see, this is the one of the special solution, right? And if you see here the non-zero components, so this is the possibility that we can get 100% possibility that we can have here a non-zero component. We can have zero component also, but we have the possibility that we can have the non-zero component also. So 1 2 3 3 non-zero components and 2 zero components. Now let's read out that there exist on in which m minus n variables are 0. So m minus n means what it is saying, that this is m minus 1 n. So m is total number of how many? Total number of m is 5, right? And n is 2, so m minus n is 3, right? So it says that at least m minus n variables are 0. कम से कम तीन जो वेरिएबल्स उसको 0 बता रहा है. बट फॉर दिस पर्टिकुलर हाउ मेनी वेरिएबल्स वी हैव गॉट 0? x3 एंड x4, राइट? तो ये बोल रहा है कि कम से कम तो 3 होगा ही होगा, बट हमको उससे भी कम मिल रहा है. दैट मीन्स कि दिस इज कंट्राडिक्टिंग. सो दिस कैन नॉट बी करेक्ट ऑप्शन, right? And option D, there exists a solution in which at least n variables are non-zero. This option is also incorrect. We can easily look at this. So let's take an example of matrix, maybe 0 2 here and 0 0. If you try to find the solution for this particular ax is equals to 0, let's suppose this matrix A is 0 and we are trying to find the solution for ax is equals to 0. So we have here 2 pivot, right, and only 1 free columns. So there would be one spatial solution, and we will set as x3 to 1, right? And what will be the other components? So we are going to do from here the back substitution from here. So we will get x2 as 0, and again you will do the back substitution and you will get x1 as 0. So what this option is saying, that there exists a solution in which at least kam se kam n variables are non-zero. So here what is n for this particular matrix? N is number of rows, so n is 2 and m is 3. So what it is saying, that you will get at least n variables are non-zero. So how many variables you are getting non-zero? One variable. And according to this we should get 2, कम से कम 2 तो होना ही चाहिए जो नॉन जीरो हो, बट हमको उससे भी कम मिल रहा है. ओनली वन वेरिएबल इज दैट इज नॉन जीरो, अदर वेरिएबल्स आर जीरो, राइट? सो दिस ऑल्सो इज कंट्राडिक्टिंग. So this cannot be also true. So only A option is true. So the moral of the story for this particular question is that you should have a good understanding of solving the system of equation Ax is equals to 0. Okay, now let's proceed with the next question. Okay, now let's look at this question number 9. So this will be our question number 9. Let A be n cross n matrix over the set of real number R. Let B be the matrix obtained from A by swapping 2 rows. So okay, so we have done this row operation. So R1 have gone into the R2 and R2 have gone into the R1. So we have just swapped the two rows and we have got this matrix B. Which of the following statement is or are correct? The determinant of B is a negative of the determinant of A. Yes, this is true, because if we swap 1 times a row, then we will have to consider the negative sign in the determinant. So this is absolutely true. The second statement, if A is invertible, then B is also invertible. So we are just swapping the row, right? And if A has the independent rows or the columns, then B will also have the independent rows and all those independent columns, right? Because from A to B, are we doing any operation that can affect the components, or no, we are just swapping the rows, right? So if A is invertible, then B will also be the invertible. So this statement is also true. If A is symmetric, then B is also symmetric. I think that should not be correct. Let's take the diagonal element as 1. We can have a symmetric matrix like, so A here, and here B, here we can have B here, and C here, C here. So this is symmetric matrix, right? If we take the transpose, we will have the same matrix, right? Now let's suppose I do the row exchange. So R2 will go to R3 and R3 will go to R2. So 1AB and BC1 and A1C, right? So clearly it is not a symmetric matrix. So this statement is false. If the trace of A is 0, then the trace of B is also 0. So no, this is also not a true. In general, rows operations affects the eigenvalues, right? So we are doing some row operations. So normally, yeah, so this statement is also not true. If the trace of like sum of the eigenvalues is 0, then we cannot say that the sum of the eigenvalues will also of B will be also 0. Right, so there are few more points about the eigenvalues that you can keep it as a fact, like this, that if you do the row operation, eigenvalues usually change. So if you are doing the row operation, the eigenvalue usually gets changed, and elimination does not preserve the eigenvalue, right? So if you, let's say if you have this matrix A, right, if you try to find the eigenvalue here, that you will get is 0 and 7, right? Because if you add 6 plus 1 is 7, so 0 plus 7 is 7, and if you take the determinant, so that is 6 minus 6 is 0, so 0 times 7 is 0. So these two are the eigenvalues of this matrix A. Now let's proceed with the elimination and let's apply this operation that so we have taken this as a pivot and we have applied the elimination and we have got this matrix U, right? And if you look at this matrix U, here we have the eigenvalue that is 1 and 0, right? So you can try yourself and you can find the matrix A's eigenvalue, and after elimination you can find the matrix U's eigenvalue. So you see, after elimination or after doing the row operations, the eigenvalue usually do not get preserved, it gets changed, right? So this is also a good point to consider as a fact, right? And here also we are doing some kind of row operations, right? So obviously we cannot sure that the trace or the sum of the eigenvalue will be same for A and B also, right? And these points are very common, that if you have this triangular matrix, then for triangular matrix the diagonal element will be the eigenvalues, and they are not the eigenvalue of A. So how you get the triangular matrix? If you have some matrix A, you get the triangular matrix after doing the Gauss elimination, you get the upper triangular matrix, right? And what it is saying, that those elements that are sitting onto the diagonal of this upper triangular matrix, those will be eigenvalues. but it doesn't mean that if these are the eigenvalue of those upper triangular matrix U, that those will be the also eigenvalue of this matrix A. Just now we have seen here, right, with this example. If you try to do elimination, it doesn't mean after applying the row operation that this matrix and this matrix will have the same eigenvalue. So this is what it is written, that the triangular matrices has the eigenvalue sitting along the diagonal, but they are not the eigenvalue of matrix A. And these are the very common points, that the product of the n eigenvalue equal to the determinant, and the sum of the eigenvalue of and the sum of the n eigen values equal to the sum of the n diagonal entries. So that is what we call the trace. So this is very well known concept to all of you. Alright, we can proceed with the next example. So this is question number 10. A matrix M is constructed by stacking 3 columns vector, that is v1, v2, v3 as. So what we are doing, we have 3 vectors and we are putting it as a column, and we are saying it as this as a matrix M. Choose the set of vectors from the following options such that rank of M is 3, right? So all these 3 vectors belongs to some 3-dimensional space, and if we are forming the matrix by putting all these vector into as a column of this matrix M, then if the rank of this matrix is 3, that means we have the full rank. That means we will have the pivot in each and every column and row, right? So all will be independent vector, and if this is the case, then their determinant should not be equal to 0. And also we can say that if we proceed with the elimination, we will get the 3 pivots, right? So you can just get the matrix and you can just find the determinant, or you can go with the elimination. So let me do with this first option. So what will be this M matrix? That will be 1 0 1, the first column, and the second column will be 0 minus 1 0, and the third column will be 1 minus 1 and 1. You can just find out the determinant of this matrix. If it is 0, then that means these columns are not independent column. That means they will not have the full rank, right? Or you can just go for the elimination also. So you can proceed anyway. So let me do with the elimination. So if this is the pivot, simply we will apply the elimination steps. So we are not doing anything with the row 2, and this will be 0. So 0 minus 0 is 0, 1 minus 1 is 0, right? So the maximum pivot we can get is these 2 pivot. We cannot have the third pivot in this case, right? So the rank of this matrix cannot be 3. So this option we can neglect, or you can just find the determinant of this matrix M. So if you do that, you will be getting minus 1. So you will get definitely 0 in this case. So minus 1, and that will be 0, and here you will have plus 1. So that will give you 0, right? So 0 determinant you are getting 0. That means it tells that these set of column vectors are not linearly independent, so they have some kind of dependency. Similarly we can do with the second option. So 1 1 1 and minus 1 0 1 and 0 0 0. Definitely 100% sure we will be getting here the determinant of M that is equal to 0, because we have the complete column with the 0 component. We can find for this third one 1 0 1 minus 1 0 and 1, and 1 minus 1 and 1, right? We can proceed with the elimination. Maybe we will take this as a pivot. So 1 minus 1 and 1. We are not doing anything with this row 2. Here we will have 0, 1 minus minus 1, that is 2, 1 minus 1 is 0, right? So at this pivot position we have this 0, so we can do this row exchange. So now the matrix will look like this. So third row is at the second row and the second row is at the third row, right? So we have this first pivot, this second pivot, and this is the third pivot. So the rank of this matrix will be 3, right? So this is the correct option for this particular question. You do not have to check for the D because you will not get the complete full rank, or the pivot will be less than 3, or in other words the determinant of this matrix for this option D will be 0. Okay, now let's look at this question number 11. This is very easy question. We have 3 by 3 matrix P with all the real elements has the eigenvalue. So we have given this the eigenvalue of this matrix P. So that is 1 by 4, 1 and minus 2. The value of the determinant of P inverse. So if this matrix P has the eigenvalue, that is lambda 1 is equals to 1 divided by 4 and 1 and minus 2, then definitely we know that the eigenvalue of the inverse of this matrix will be lambda 1 is equals to 4, because and lambda 2 is equals to 1 divided by 1, that is 1, and lambda 3 is equals to minus 1 divided by 2, right? So we just have to find the determinant, right? So determinant, if we know the eigenvalues, then determinant is nothing but the product of these eigenvalues. So 4 times 1 times minus 1 divided by 2, so that will get cancelled. So minus 2 is the correct answer for this question. So you just need to know if A has the eigenvalue lambda 1, then A inverse will have the eigenvalue 1 divided by lambda 1. That is all.